Hello everyone, my name is Neha. I am a student of BSc Chemistry Honours 3rd semester and I am here for making a video for visually impaired students from the book Modern, written by S. Kiran for the subject of physical chemistry. Today we are going to cover the topic distribution law. So let's get started. Nernst distribution law definition. Nernst distribution law studies the distribution of a solute between two immiscible solvents in contact with each other. When a solute soluble in two immiscible solvents is added to a mixture of these solvents, the concentration of solute in both the solvent layers is indifferent. In other words, the solute distributes itself in both the solvents. For example, when a dilute solution of iodine in water shaken with carbon tetrachloride, the iodine distributes between two immiscible solvents. Iodine is about 86 times more soluble in carbon tetrachloride than in water. Due to higher solubility, most of the iodine passes into CCl4 layer. In simple words, iodine is distributed between two immiscible solvents, water and carbon tetrachloride. Nernst in 1891 showed that when a solute is added to a mixture of two immiscible liquids in both of which it dissolves, then it distributes itself between both the liquids in such a way that the ratio of concentrations of the solute in both the liquids remains constant at constant temperature. However, this ratio is constant only when the solute has same molecular state in both the solvents. That is, the solute neither undergoes association nor dissociation in both these solvents. The generalization put forward by Nernst is called Nernst distribution law and is stated as a solute distributes itself between two non-miscible solvents in contact with each other in such a way that at equilibrium, the ratio of the concentration of the solute in the two layers is constant at a given temperature, provided the molecular state of solute is same in both the solvents. If a solute X distributes itself between solvents A and B as in figure 1, the distribution law is written as concentration of X in solvent A upon concentration of X in solvent B is equals to C1 upon C2 is equals to C1 upon C2 is equals to K. The constant K is termed as the partition coefficient or distribution coefficient. Factors affecting partition coefficient: nature of solute, nature of liquid pair, temperature. Nature of solute: for a particular liquid pair, different solutes have different solubility, hence the value of partition coefficient will be different for different solutes at a given temperature. It is clearly seen from the data in the table below. Nature of liquid pair: a given solute has different partition coefficient in different liquid pairs as shown in the table below. Temperature: the solubility of a solute in a particular solvent changes with temperature. As the temperature is changed, the solubility of a solute in a given liquid pair also changes. Therefore, the partition coefficient also changes with temperature. The change in value of partition coefficient K for 1 degree rise in temperature is known as temperature coefficient. However, the value of temperature coefficient is generally small. Table below shows value temperature coefficients for some systems. Experimental verification of distribution law. Solutions of iodine in carbon tetrachloride of different concentrations are shaken with water taken in different bottles. These are allowed to stand undisturbed till the two layers separate out. A known volume of CCl4 layer and aqueous layer is pipetted out and titrated against standard sodium thiosulfate solution, and the concentration of iodine is determined. The following results from the distribution of I2 between CCl4 and water show the constancy of ratio of concentration in each layer, hence prove the validity of distribution law. These results show that the ratio C1 by C2 is almost constant, hence the distribution law is valid in this case. Conditions for validity of distribution law, limitations of Nernst distribution law. The distribution law in its simple form, that is K is equals to C1 by C2, does not hold under all conditions. Some limitations and the conditions under which the law is applicable are as follows. Temperature should be kept constant. The solubility of a solute in both the liquids changes with change in temperature. This may result in change in concentration in both the solvents. Moreover, change in temperature may affect the mutual solubility of the two solvents. Therefore, with change in temperature, a different value of partition coefficient is obtained at every temperature. Hence, the temperature should be kept constant throughout the determination of partition coefficient. The two solvents should be immiscible or sparingly soluble. The mutual solubility of two solvents should be affected by addition of solute. The solutions should be dilute. Distribution law holds good for dilute solutions. As the concentration of solute increases, the deviations from distribution law become more and more pronounced. The molecular state of solute should be same in both the solvents. This law is not valid under following two conditions. When the solute undergoes association. The law in simple form is not applicable when the solute undergoes association in any of the solvents. For example, distribution law does not hold for phenol distribution between benzene and water because phenol undergoes association in benzene to form dimers. When the solute undergoes dissociation, the distribution law is also not valid for solutes which undergo dissociation in any of the solvents. For example, electrolytes like HCl undergoes dissociation in water, and hence its solution is in a mixture of water and an organic solvent, benzene, CCl4, CH2, etc. does not obey distribution law in its simple form. Modification of distribution law with change in molecular state of solute. Nernst showed that the ratio C1 by C2 is constant, that is K is equals to C1 by C2, is applicable only when the solute has the same molecular conditions in both the liquids. That means the solute does not undergo association or dissociation in any of the liquids. However, if any of such change takes place in one or both the liquids, then the distribution law gets modified. Let us consider cases in which a solution may associate or dissociate or enter into chemical combination with one of the solvent. Case 1. When solute undergoes association in one of the solvents. Suppose a solute X remains in the normal molecular state in phase 1, whereas in phase 2 n molecules of X undergo dissociation. Undergo association to form complex molecules Xn as shown in figure 2. Solute X undergoes association in solvent 2. Here two equilibria exist simultaneously, that is X changes into X, phase 1, N molecules of X give Xn. Phase 2. Suppose the total concentration Suppose the total concentration of solute X in phase 1 is equals to C1. The total concentration of solute X in phase 2 C2. If alpha is the degree of association of solute in phase 2, then the concentration of associated molecules in phase 2, that is concentration of Xn, is C2 alpha upon 1 upon N. Therefore, the concentration of normal molecules in phase 1 minus alpha into C2 . Applying distribution law to the distribution of X in the two solvents, we can write concentration of X in phase 1 upon concentration of normal molecules of X in phase 2 is equals to K, that is C1 upon 1 minus alpha into C2 is equals to K. Applying law of chemical equilibrium to the polymerization process, NX changes into Xn, we can write the equilibrium constant Keq as concentration of associated molecules in phase 2 upon concentration of normal molecules in phase 2 raised to the power n is equals to Keq. Or 1 by n C2 alpha upon 1 minus alpha into C2 raised to the power n is equals to Keq, taking nth note on both sides, and however, when the molecules in phase 2 are completely associated, that is alpha is equals to 1, the equation becomes C1 upon n under the root C2 is equals to constant. This relation is used in determining the value of n, the extent of association of molecules. The values of C1 and C2 are determined experimentally and substituted in equation 4. Putting n is equals to 1, 2, 3, etc. The value for which a nearly constant value of k is obtained is equal to n. Equation 4 has been verified by studying distribution of benzoic acid between water and benzene. Benzoic acid exists almost entirely as dimers C6H5COOH whole twice in benzene, but in normal state in water. Evidently, the ratio C1 upon C2 is not constant. Hence, benzoic does not exist as single molecule in benzene. A fairly constant value of C upon under the root C2 shows that the benzoic acid exists as dimers of benzene. The method to calculate N has been explained in section 8.0. Case 2. When the solute undergoes dissociation in one of the solvents. Let the solute X dissolve in phase 1 in its normal state and undergoes dissociation in solvent 2 as shown in figure 3. The two equilibria existing simultaneously are total concentration of X in phase 1 C1, total concentration of X in phase 2 C2. The degree of dissociation of solute in phase 2 is equals to alpha. Therefore, the concentration of undissociated molecules in phase 2 is equals to 1 minus alpha into C2. Applying distribution law, the ratio of concentration of solute in equilibrium 1 is given as C1 upon C2 into 1 minus alpha is equals to K. On the other hand, When the solute is dissociated in phase 1 having degree of dissociation A, dissociation alpha, and remains undissociated in phase 2, then the partition coefficient is given by C1 into 1 minus alpha upon C2 is equals to K. Case 3. When the solute is dissociated in both the solvents, it is evident from the figure 4 that the concentration of the solute in layer 1 is C1 1 minus alpha, and then layer 2 is C2 1 minus alpha. Is C2 into 1 minus alpha, where alpha is the degree of dissociation of the solute. The partition coefficient is given by C2 into 1 minus alpha upon C1 into 1 minus alpha is equals to K. Case 4. When the solute enters into chemical combination with one of the solvents. Suppose the solute X remains in normal molecular state in solvent 1, but one molecule of X combines with n molecules of solvent in phase in phase 2 to form X dot NS molecule, figure 5. Following equilibria exist simultaneously. Let the concentration of solute X in normal state in phase 1 is equals to C1, the concentration of X in normal state in phase 2 C2, concentration of solvent molecules in phase 2 CS, concentration of complex molecules in phase 2 CC. Applying distribution law to equilibrium 1, we get C1 upon C2 is equals to K. Applying law of chemical equilibrium to equilibrium 2, we get CC into CC upon C2 into CS raised to the power n is equals to K1. In dilute solution, the concentration of solvent. In dilute solution, the concentration of solvent in phase 2 is in excess, therefore its concentration CS remains practically constant. Thus equation 2 takes the form C1 upon C2 is equals to K1 into CS raised to the power n is equals to K2 constant. Adding 1 to both sides, 1 plus C1 upon C2 is equals to 1 plus K2 is equal to C2 plus C2 plus CC upon C2 is equals to 1 plus K2. Dividing equation 1 by equation 2, we get C1 upon C2 into C2 upon C2 plus CC is equals to K upon 1 plus K2. C1 upon C2 plus CC is equals to K upon 1 plus K2 is equals to K3 is equals to K3. C2 plus CC is equals to total concentration of normal molecules and solvated solute molecules in phase 2. Therefore, equation of 4 may be written as total concentration of solute X in phase 1 upon total concentration of solute X in phase 2 is equals to constant. It is evident that when the solute molecules enter into chemical combination with solvent molecules, the distribution law does not get modified. However, there is change in the numerical value of the constant. Thermodynamic derivation of the distribution law. Thermodynamic derivation of the distribution law. The derivation of distribution law from thermodynamics is based on the condition that in a phase equilibrium between two immiscible liquids containing the same solute dissolved in them, the chemical potential of the solute must be same in both the phases. Suppose a solute is present In two immiscible solvents A and B in contact with each other, the chemical potential in solvent A is mu A and in solvent B is mu B. At equilibrium, the chemical potential of the solute in both the phases is equal. That is, mu A is equals to mu B. From thermodynamics, we know chemical potential of a substance is given as mu is equals to mu naught plus RT ln A, where mu naught is the standard chemical potential and A is the activity of the solute in solution. Therefore, mu A is equals to mu naught A plus RT ln A of A, and mu B is equals to mu B, and mu B is equals to mu naught B plus RT ln AB for phase B. Hence, mu naught A plus RT ln A is equals to mu naught B plus RT ln A B. RT ln A upon A B is equals to mu naught B minus mu naught A. Ln A upon A B is equals to mu naught B minus mu naught A upon RT. At constant temperature, the standard chemical potentials mu naught A and mu naught B for a given solute in a particular solvent are constant. Since R is also constant, it follows from equation 5 that ln A upon AB is equals to constant. A upon AB is equals to constant. Since the solutions are dilute, therefore the activities are equal to the concentrations. So equation 7 becomes concentration of A upon concentration of B is equals to constant. This is a Nernst distribution law. It is applicable in this form when the solute is normally distributed in both the layers. However, it gets modified in the cases when the solute undergoes association, dissociation, or enters into chemical combination with one of the solvents. Applications of distribution law. There are many applications of distribution law in laboratory and in industry. Some of these are briefly discussed here. In calculating solubility of a solute in a solvent. When a solute is taken with two immiscible solvents in contact with each other, at equilibrium both the solvents are saturated with the solute. Therefore, the concentration at equilibrium are equal to the solubility of solute in both solvents. Distribution indicators. Certain solvents can appreciably dissolve even the small amounts of solute present in some other solvent. When such a solvent is added to a dilute solution of the solute in some other solvent, most of the solute gets distributed into the solvent. Hence, it acts as an indicator for the presence of even a small amount of the solute. For example, a dilute solution of iodine in water is almost colorless. Iodine is considerably soluble in CS2. Its distribution coefficient between CS2 and water is 400. Therefore, an extremely dilute solution of iodine can be estimated by adding a few drops of CS2 to its aqueous solution. A sufficient amount of iodine passes into CS2 layer and gives it a deep violet color. This solution may be titrated against hyposodium thiosulfate solution till the violet color in CS2 layer disappears. Hence, CS2 can serve as distribution indicator in iodometric titrations in which iodine is produced during titration. In determination the extent of association or dissociation of a solute in a solvent. Using distribution law, the molecular state of a solute in a solvent can be determined. In the distribution experiment, if the ratio of concentrations of solute in both the solvents, that is C1 by C2, is constant, then the solute behaves normally in both the solvents. When a solute X undergoes association in one of the solvents, NX in equilibrium with Xn, having concentration C2 in it, then the distribution law modifies as C1 upon N under the root C2 is equals to K. From the value of n, the molecular mass of the solute in the solvent can be calculated by multiplying the actual molecular mass by n. For example, benzoic acid in a mixture of water and benzoic exists as dimer in benzene. Hence the value of n is equals to 2. Therefore, the molecular mass of benzoic acid in benzene is 2 into 122, that is 244. The value of n in above expression can be calculated by one of the following methods: by Hayden trial method and logarithmic method. In the study of chemical equilibrium involving formation of complex ions, an important application of distribution law is to study equilibria involving complex ions. Consider some reactions involving formation of complex ions. In the process of extraction. Another important application of the distribution law is in the process of extraction in laboratory as well as in industry. In laboratory, for instance, it is frequently used for the removal of a dissolved organic substance from aqueous solution with solvents such as benzene, ether, chloroform, carbon tetrachloride, etc. The advantage is taken of the fact that the partition coefficient of most of the organic compounds is largely in favor of organic solvents. In industry, the process of extraction is used to remove the impurities from the product. The aqueous solution of the substance to be extracted is shaken with an organic solvent in which it is highly soluble. After shaking vigorously, the mixture is allowed to stand for some time. The two layers are then separated using a separating funnel. The organic solvent is recolored by distillation and used again. For the extraction process to be recolored by distillation and used again. For the extraction process to be more efficient, following conditions should be fulfilled. The distribution coefficient of the substance between the extracting solvent and the solvent in which it is already dissolved should be very high in the favor of extracting solvent. Sometimes the distribution coefficient in the extracting solvent is artificially increased by making the substance less soluble in the aqueous phase. This can be done by adding some substance which decreases the degree of dissociation of the compound in aqueous phase. For example, acetic acid, which weakly ionizes an aqueous solution, is to be extracted with ether. A strong acid, say HCl, is added to the solution. Due to ionization of HCl, the H plus ions concentration increases, and due to common ion effect, the ionization of CH2COOH is suppressed. As a result, there is greater concentration of ionized acetic acid, hence greater amount of acid will be extracted in ether layer. Similarly, the extraction of organic base from its aqueous solution into organic solvent can be increased by adding strong inorganic base. In general, the solubility of an organic compound in water can be decreased by adding salts, hence its distribution coefficient increases in favor of extracting solvent. This is termed as salting out effect. Thus, we conclude that greater the distribution coefficient in the favor of organic solvent, greater will be the amount extracted. To recover the maximum amount of substance, the extracting solvent should not be used in one lot, rather it should be used in maximum number of installments. This is called multiple extraction or multi-step extraction. The fact that it is more efficient to use extracting solvent in small portion rather than in one lot is illustrated as follows. Application of distribution law in determining the degree of hydrolysis. Aniline hydrochloride is a salt of weak base aniline and a strong acid HCl. Its degree of hydrolysis is determined as follows. Step 1. Determination of hydrolysis constant. Aniline hydrochloride is hydrolyzed according to the reaction. C6H5NH3Cl plus H2O gives out C6H5NH3 positive OH negative plus HCl. Acid set free. Acid set free. The hydrolysis constant is given as C6H5NH2 plus H2O free aniline. KH is equals to free aniline into free HCl upon unhydrolyzed salt is equals to C6H5NH2 is equals to concentration of C6H5NH2 into concentration of HCl upon concentration of C6H5NH3Cl. To calculate the above concentration, an aqueous solution of aniline hydrochloride of non-concentration is shaken with a non-volume of benzene. On standing, the mixture separates into two layers. Free aniline get distributed between water and benzene, while HCl and unhydrolyzed salt remain in the aqueous layer as shown in figure 6. Determination of concentration of free aniline in the aqueous layer. A non-volume of benzene layer is taken out and the solvent is evaporated. Then the weight of aniline left behind is found. From this, the concentration of aniline is being in benzene layer is calculated. The concentration of aniline in aqueous layer can be calculated using distribution law. Determination of concentration of free HCl in aqueous layer. From hydrolysis reaction, it is clear that number of moles of HCl set free is equals to total number of moles of aniline produced. Further, total amount of aniline produced is equals to amount of aniline present in aqueous layer plus amount of aniline in benzene layer. The concentration of free aniline in aqueous and benzene layer is calculated in step 1 above. From these values, the number of moles of free HCl produced is also calculated from the volume of aqueous layer and the number of moles of HCl. The concentration of free HCl in aqueous layer can be calculated. Determination of concentration of unhydrolyzed salt in aqueous layer. Again, from hydrolysis equation, it is seen that the number of moles of aniline hydrochloride hydrolyzed is equals to total number of moles of free aniline or HCl produced. The quantity of RHS has been calculated. In step 3 above. Therefore, the number of moles of aniline hydrochloride hydrolyzed is obtained. When this is subtracted from the initial number of moles of the salt, the number of moles of unhydrolyzed salt can be calculated. From the volume of aqueous layer, the concentration of unhydrolyzed salt can be calculated. Substituting the values calculated in steps 1, 2, 3, 1, 2 and 3 in equation 1, the hydrolysis constant pH of the salt can be calculated. Calculation of degree of hydrolysis of aniline hydrochloride. After calculating the hydrolysis constant KH as discussed above, for a solution of the salt having concentration C moles per liter, the degree of hydrolysis can be calculated using expression H is equals to under the root KH upon C. That's all for this video.